While we're on the word integral, I'd like to also show you a new substation design that has been applied in greenfield sites called an integrated unit substation. In this case, we have one assembly for both the primary and the secondary switchgear for the substation. You can see in the photo on the left that we again are applying the medium voltage vacuum miniature circuit breaker with integral trip unit, but in this case in a draw-out design that's mounted on the lower section of this assembly. The lower compartment is fully isolated from the upper compartment, which actually serves as the low voltage switchgear section. So following the power flow in the section view on the right, you can see my incoming cable would come in from the top in the darker green, move into the medium voltage breaker, and back through the breaker into the transformer compartment. And I show PTs and CPTs in this section as well. And then the secondary of the transformer is on the same side and comes back into this enclosure, feeding into a low voltage main power circuit breaker, which then feeds low voltage bus and feeder breakers. Now you might be asking yourself right now, who would manufacture a transformer with both the line and load spades on the same side? Well, the answer is at least two manufacturers that I know of. And here we've shown a drawing of a typical, actually liquid-filled substation transformer with the primary spades on the lower right-hand portion of the assembly and the secondary spades on the upper right-hand portion of the assembly. We insert the integrated unit substation onto the side, and as you can see, we have 15 kV coming into this assembly and 480 volts coming out, ultimately feeding, in this case, 4 feeder circuit breakers. On this slide, we're showing you the advantage of this assembly, basically space. In this case, showing the before, where we had a fused load break switch in the primary and a dry type transformer connected to secondary switchgear. We were able to get rid of the primary fused load break switch, install an IUS on the primary, serving both as the primary breaker and also the secondary switchgear, rotate the transformer so that the footprint of the overall assembly is not as wide, and end up with an assembly that's about 45% smaller in footprint than my traditional designs. In the lower diagram, you'll notice I'm using the vacuum medium voltage breaker on the primary, but I also show a secondary low voltage main circuit breaker. I would probably opt to remove this breaker from the assembly and instead install current transformers, tripping the primary breaker as we've discussed before. So let's summarize what we've discussed today. Let's take a look at, if we had a blank piece of paper, what would today's perfect unit substation look like? Well, I've included here at least my idea of a perfect unit substation. As you can see in the one line, it's fed from a 15 kV source into a load break switch and a primary vacuum circuit breaker with an integral 5051 tripping device. Followed by that is the transformer, and then feeds the low voltage section, which includes no main breaker but secondary current transformers, and in this case 4 feeder breakers, each with LSI trip units. The primary vacuum circuit breaker is actually controlled via 2 relays, one an integral tripping relay protecting the secondary bus with the appropriate short time settings to coordinate with the feeder breakers on the secondary, and 2 via a separate 5051 protective relay on the primary connected to primary CTs set to protect the transformer. The integral trip unit in the primary vacuum breaker would also include the arms function, allowing me multiple settings groups so that I could set up a maintenance mode in the event that I needed to work on or rack in and out the secondary power circuit breakers in this substation. I would also include the arms feature in each of the 4 secondary feeder breakers, allowing me to set up a maintenance mode so that operators working in downstream energized equipment could work in lower level PPE in the maintenance setting. Finally, you'll notice on this one line I've also included a dotted green line that connects the primary breaker with all of the secondary feeder breakers in a zone selective interlocking scheme, so that in the event of a fault within the zone, the breaker nearest the fault will trip without any intentional delay. On the right of this slide, I'm showing the low voltage switchgear elevation that corresponds with the one line at the left. I slipped one extra thing in here on you. As you can see, I have some room in the first vertical section at the bottom to install a high resistance grounding system. This HRG system installs a resistance between the neutral and ground connection on my low voltage power distribution, allowing me to reduce the opportunity for an incident of a line to ground fault. Beyond the scope of today's discussion, but in my view, again, an excellent safety feature that should be considered for future designs. So before we close out, let's take a quick snapshot of our before and after substation. Before, the workhorse of the industry involved a fused load break switch on the primary with no secondary main, and after, we actually have changed that fused load break switch to a switch and an integral vacuum circuit breaker, again with no secondary main. As you can see, the itemized list in the lower left gives us some advantages. First, we can have more than 6 feeders. The 6 circuit rule doesn't apply anymore because I have secondary bus protection. And also because there's secondary bus protection, I have both overload and better short circuit protection of that bus. We've added zone selective interlocking, or ZSI protection, in this substation, allowing us to trip the nearest upstream breaker to the fault with no intentional delay. And finally, because I've added secondary bus protection, I can more safely rack feeder breakers from an energized bus, knowing that in the event of a fault, I'll clear the upstream device, the vacuum circuit breaker, much faster. This allows operators to reduce the amount of PPE that's required during maintenance of this equipment. I promised earlier to show you the economics of some of these new designs, and I'll do that here. What I've shown here is an example of the 1500 kVA substation we've reviewed earlier, and as you can see, without being too commercial, we've just used percentages for this assembly as a substation itself. The first example is with no secondary main, with a medium voltage load break fuse switch, transformer, and low voltage switchgear. And as you can see, we'll call that the combination of those 3 components a total of 1. If I add a secondary main breaker to this assembly, and I would recommend that we do this today whether we use the new designs or not, there is an incremental cost. Adding that breaker brings us up to a total of about 1.09, or perhaps 9% higher, with an added cost in the low voltage switchgear. Depending on the rating, you may also add to the footprint of this assembly. In my example, at 2000 amp bus, it's not necessary to add another vertical section. And finally, at the very bottom right of this slide, the new approach using a primary vacuum breaker, the medium voltage transformer and low voltage assembly comes out at 1.07. So it's fairly clear that we have almost a push, actually maybe some savings, of the secondary main breaker approach with the fused load break switch primary, as opposed to including a vacuum breaker in the primary used to protect both the primary and the secondary bus. The integrated unit substation, which we spoke of earlier, would also be at about the same price point as the primary vacuum breaker design, but with the advantage being a smaller footprint. Before we finish up here, I'd like to leave you with a provoking thought. This slide shows the life cycle of any facility, whether it's industrial or commercial. Starting from the left to the right, we have a business justification of the facility, and then a design. Ultimately, we build the facility, we operate and maintain it, and finally, at its end of life, we have to dismantle and recycle it. If we take a look at these 5 different steps, from the standpoint of protection versus prevention, you can see that most of the codes and standards that we live with today really reside in the area of protection. How do we effectively install it? How do we safely install it? After it's installed, how do we safely operate it or maintain it? The NEC, OSHA, MSHA, NFPA, NIOSH, all really are retrofit type standards that are designed to deal with the equipment after we've designed it and put it into the field. I would submit to you that it's critically important for all of us as design engineers to think about the responsibility incumbent upon us in the design process. When we design power distribution systems today, we have a one-time opportunity to move electrical safety and reliability upstream, to move from a protection-based strategy to a prevention-based strategy, using safety by design as the central approach. It's onerous to think about it, but the users of this equipment will have to live with your design in terms of maintaining and operating it for the next 40 or 50 years. So the decisions you make today are important for the future. I'd like to thank you very much for taking the time to listen to our Launch and Learn presentation today. I'm hopeful some of the concepts we've introduced will provoke some thought and drive you towards a different thinking process in designing power distribution substations. I'd certainly like to hear from any of you. If you have some questions or comments, feel free to send me an email at the address below, and I'll respond. Again, thank you for your time, and thank you again for your interest in Eaton products, services, and solutions.